All right, so we're going to graph the lab data from yesterday, calculating the moment of force for the door. In the physics lab, bless you. So one of the notes that you might have seen me write on your graphs this year is, use well more than half the page, use most of the page. Like the graph should be basically the entire page. A little bit of room to, clearly label your axes here. And so you kind of want to start with, what does theory suggest here? The moment of force is equal to force times distance to pivot. All right. Really, the full form of this equation is sine theta, where theta is the angle between these two vectors. So this is a cross product or a vector product. So torque itself is a vector. You can multiply two vectors and get a vector. That's called a cross product or a vector product. If here's the pivot, the hinge of the door, and we're applying forces at different places, there's a certain fixed amount of torque required to open the door, of moment required to open the door. And we could either apply a lot of force a tiny distance away, or as we increase R, right, the force required gets sort of less and less. And so we need a littler force here, a littler force there, the most force sort of there. So that's sort of the nature of this lab. Let's see, I guess the force is decreasing, so we're getting smaller and smaller. So that's sort of the physics there, right? The product of these two things is going to always equal that. The independent variable is the distance, and the force required sort of at that distance depends on how far away we are, right? That's sort of what the theory suggests here. So we want to reorganize this, and the sine theta, if we're applying the force at a right angle, everybody with a calculator right now should take one out and prove to yourself why this always works, but if we're applying a force at a right angle, this sort of goes away. Because what's the angle between the force and the displacement vector here? 90 degrees. What's the sine of 90 degrees? If you don't know, put it in your calculator, it equals 1. Because sine 90 is 1 times this is just this, right? And so when it's already at a right angle, this kind of doesn't matter. Sometimes the force is applied at some other angle, right? And only the perpendicular component of force, like if we wrote this F sine theta, would be the perpendicular component of force, relative to that displacement vector. So we want to sort of realize that term doesn't matter here. We applied the force always at a right angle as we collected the data yesterday. We turn this into the equation of a line where the dependent variable, in this case the force, is going to be isolated, on the y-axis. We're going to plot it on the y-axis. So we want it to be sort of like in the form y equals mx, the familiar equation of a line. So we divide each side of this by r, and then we rewrite it as force equals the moment of force required times 1 over r. So just sort of separate this fraction out. So now I can see this as y equals mx. Now, you shouldn't do this on your graph paper, right? We kind of want to use the graph. But usually there's a lot of, since we know it's going to be linear, there's going to be a lot of space here. I think we only collected 3 data points. So we're plotting this on the y-axis. So I'll label that force measured in newtons, right? Quantity with the units. And on the x-axis, I'm plotting 1 over r. So it's the inverse of the distance. And so that's going to be measured in reciprocal meters. So meters to the -1, right? Because it's 1 over a distance. Looking at the range of values, the x-axis goes from like 1.5 to 5.5 reciprocal meters. And so we use a true 0 here, and we want the highest value to be around 6. That'd be about 3. So it's like maybe 0.2, 0.2, 4, 6, 8. So that would be 1, 1.2, 4, 6, 8, 2, 2.2, 4, 6, 8, 3. And I'm not really committing to that yet, but I'm just sort of marking off every. But I think that's pretty good. If I'm at 3 right here, I'll be at 6, well more than half the page. So I am going to commit to that scale. Every square is 0.2. So I like to kind of label at least the first square, because then I remember, okay, that sets my scale. Every square represents 0.2 reciprocal meters. Then I can just kind of label these as 1, 2, 3, 3.2, 4, 6, 8, 4, 4.2, 4, 6, 8. 5.2, 4, 6, 8, 6. My highest, sort of value is 5.5, so I'm well more than half the page on the x-axis. So another note that you might have read in your sort of graphing work is rescale x or y axis to spread the data out over more than half the page. So when you set the scale, it's important to take the time up front to sort of make this the way that it should be, so all the data just sort of falls in place as it should. And then the forces range from 78 to 219 in this class. You can see some of the data that was collected in other classes on the whiteboard right there. And the trend is certainly there, but I don't know if I just must have had more energy first period and I pushed with the greater forces. Like 219 was the max force required there. I think in the other classes it was like less force, for that sort of first data point. So we'll scale it all the way from now here's where I suggested yesterday for those of you that were present. I don't know if it was a skip day and everybody else didn't get the message, or I understand there was some kind of PSAT testing on campus. Maybe that's where you were. I don't know. But break the graph is what I suggested, because you don't want a lot of dead space in the graph. You don't want to have a true 0 and then there's no values from 0 to 78. So I might make the first one like 75 or something right here. And kind of go up from there, trying to get to like 225 maybe by here. So like I want to go up by 25, but like how many? So maybe by 5. So 80, 85, 90, 95, 100, 105, 10, 15, 20, 25, 30. 200 would be there. Well, I gotta get to 220. I think that's it. 205, 10, 15, 20, 25. So, that's more than half. So you sort of look at the scale and there's, it's kind of trial and error. Think about sort of what seems reasonable, but nice round numbers. Like the only odd number is the one I just chose, 5. So I'm starting at 75 here and I choose to go up by 5 newtons every square. So I'm just going to mark them out. 80, 85, 90, 95, 100, 105, 10, 15, 20, 125. 30, 35, 40, 45, 150, 55, 60, 65, 70, 175, 200, 205, 10, 15, 20, 225. And that captures the range of data. And it's more than half the page. And so that's the sort of the first critical step, having a good analysis. We plot data by hand here to kind of see what's going on with the science. These things are inversely related, right? As we make the force bigger, the distance is smaller and vice versa. So in order to get this positive correlation, we just did a little bit of algebra and said, well, let's just, plot 1 over r, right? So it's the inverse of the distance. And so the first one is, I'm going to plot it in sort of the order going from left to right. So the opposite order we collected the data in. It doesn't matter because it's just going to fall into place, right? So I'm going to plot the points 1.5, 78. So 1.24, so it's right in between these two. And so even though I scaled my axis to go up by 0.2, I have to use my judgment to say, well, where is 1.5, right? It's going to be directly in between 1.4 and 1.6. So 1.5, then I go up, 78? Like that's 75. That's 80, so it's like right there. A small cross. And I should probably use pencil to plot the data, but that's fine. The next one was what, 2.4. Is that 157? Somebody that's closer to that chalkboard, help me out here. Yeah. 157. So 2.4 is exactly on this line. And then 157 is 155, 67 will be about there. So yeah, there's a trend there. You can draw a line between 2 points, but let's see if the trend continues. 5.5 would be here, and it goes up to 219. So that's 205, 10, 15, 20. So just below that line. And it looks like, well, is there a curvilinear trend here? Or maybe this is an outlier, that middle point, and maybe we should have tested each point several times and averaged it. So that might have given us sort of a tighter fit there, but there's definitely a positive correlation. There's 3 points there. And so I'll sort of choose a trend line. A lot of you are forcing the graph to go through the origin, and that's not necessarily what you need to do. Just look at the actual data points and choose sort of what seems to represent the trend there. Even though We all may have scaled our axes the same just now, plotted the same data. Here's where our answers will diverge. So here's where it's like, if you're absent and you ask a colleague, hey, can I see the data from yesterday? You know, see maybe how they scaled their axes to get an idea like, oh, how did you decide to do this? Oh, go up by fives. Okay, that makes sense. You know, and that can kind of help you. But then once you go to sort of get to this step, your best fit line is probably going to be different. And you have to just, at that point on, do it for yourself. Don't just copy whatever points they chose, because they, you know, oftentimes they don't correspond to the line that you drew. So here's where sort of everybody's answers diverge, because we all use our own judgment about where the best fit line is. So that's my line. You know, you draw a single line, use a straight edge. That's a note that I'll write sometimes, you know, use a straight edge. Don't try to just do it by hand. If you need a straight edge, you need a clear plastic ruler so you can see your data points before you commit to a line. I have some back here, you can borrow one. People watching, you know, on YouTube are like, well, I don't have access to that. It's like, well, find a straight edge, use a book, you know. I know that you're industrious out there, YouTube, so figure it out. This point right here is pretty good. So I'm looking for a point that intersects the gridding of my graph picker, and it's on my best fit line. That point is more accurate than that point. Even though I collected data there, this line represents the trend in 3 data points. And so it's more accurate than any single data point. That's why you'll see me write, don't use data points to calculate slope. If that's what we were going to do, we'd only need to collect 2 data points, right? We collect these 2 and calculate the slope based on that. What we really want is 7 or 8 or 100 data points, right? And see that, oh yeah, there is a trend, you know, there's a scatter about sort of the best fit line that represents the trend in the data. So that's sort of where we're heading with scientific analysis. So this point has coordinates 3, 155. And because I just clearly scaled my axes, it's easy for me to read off what those points are. And I write the coordinates down. So, you know, I can sort of follow my working later. So if I make a mistake with slope, which sometimes students do, they'll mix up X and Y. So they'll write the sort of the Y coordinate first. So it's the X coordinate first, right? And then the Y. And then try to find a point that's also more than half the page away from it. So I chose one sort of in the middle. Here's a pretty good point down here. That one's pretty decent. This one right here is even better. All right, so this one's well more than half the page away. And this one has coordinates of 5.2, 230. So even though that's more force than we ever measured, you can extrapolate based on that trend line. So that's, you know, another sort of point of, you know, it's okay to have a little bit of space sort of above there, because maybe you could extrapolate out, or you could find a point that's sort of up there, because we're sort of assuming that there's just a linear sort of trend between this, you know, as the theory suggests, right? That's the equation of a line, y equals mx. So because this term is equal to the slope, and I can calculate the slope, I can reach a valid physics conclusion. What is the moment of force required to open that door at any point, right? At any one of these inverse distances, I know how much force is required based on the trend line. All right, everybody's anxious to calculate the slope. I can feel it in the room. Settle down, everybody. I edited that out so YouTube doesn't hear the commotion here right now, but I'm gonna start writing you guys up if that continues. Somebody just open their journal very loudly, or somebody maybe click a button in their calculator, but settle down. We're all excited about it. Me more than anybody. We've got to maintain our composure. 75 over 2.2. Don't leave your conclusion like that, please, because there's a decimal in the fraction. How do you simplify that? Calculator check. 75 over 2.2. I think we can all use a calculator check right now, right? Start the second 9 weeks out strong. So I'm getting for a slope here 34.09, but I'm going to sort of disregard those as insignificant digits and report my final answer as the moment of force equals 34. And what are the units? I'd go back up to this original equation. Newtons of force times meters of distance, right? It's more confusing to realize here that 1 over r is measured in reciprocal meters. So when we do the rise over run, the rise is in newtons, but the run is in reciprocal meters, right? So the meters sort of go back up to the numerator, and the units of moment are Newton meters. So clearly report your final answer. we're going to get in the habit of making a claim. Claim is that's the moment of force required to open the door to the physics lab. The evidence is this graph, right? So that's my evidence, because the reasoning is theory suggests this. So if I vary R and therefore 1 over R and measure the force, I can plot a graph, see that there is indeed a trend between those things. And this term tells me how this quantity varies to give me this one. Right, so you just sort of step back through what I did to sort of reach that conclusion. So claim, evidence, reason. The claim is usually a number, right? It's the conclusion to the lab. The evidence is your graph, right? Representing the data you collected, your judgment about the trend line. And the reasoning will always start with, because theory suggests this, I can measure this, right? I can vary some independent variable. I can measure some dependent variable and plot a graph and see what the trend between them is. These are the graph rules with Dr. Schleith. We'll see you next time.